This is 6.7, section 6.7, part 2's video. As an isotope of lead, 201 Pb, has a half-life of 5.2 hours, how many hours ago was there 25% more of the substance? Round your answers to 2 decimal places. Well, the first thing that we've got to do is, they've told us it takes 5.2 hours to reach its half its life. So we're going to use, you know, this equation, right? A sub 0 times the e raised to the kt. So the k is going to be the minus the natural log of 2 over the 5.2, right? And what that's going to give us is negative 0.1333. Okay, so that's going to be our decay rate. Now, here's the tricky part. And I say here's the tricky part. We want to know how many hours ago was there 25% more of the substance. Well, your y would be 1. Your initial amount would be 1.25. Now, if you think about 1 being 100% and 1.25 being 125%, right? 25% more, then the 1 and the 1.25 makes, I hate to say makes sense, but it makes sense. Okay. Times e to the negative 0.1333. And we want to go t. Well, we're going to divide both sides by 1.25. That's the first thing we're going to do, because what we want to do is isolate our exponential e. So we're going to have, let's see, we're going to have 1 over 1.25 equals e to the negative 0.1333, yep, t. Now, what you should know and have learned based upon what you've done in exponentials now is, in order to get rid of an e, you got to take natural log. So what we're going to do is take natural log of this side and take natural log of this side. These are going to cancel. So we'll scoot this down just a little bit. So what we'll be left with is a natural log of 1 over 1.25 equal to negative 0.1333t. And of course, guys, we're to sum for t, right? So we'll divide both sides by negative 0.1333. And in doing so, that cancels out here. My t now is going to be the natural log of 1 over 1.25 divided by negative 0.1333. Well, when you take the natural log of 1 over 1.25, it's going to give you a negative number, right? And when you divide it by the negative 0.1333, then what you're going to get is 1.674. Now, I would do the natural log of 1 over 1.25, hit enter. It gives me a negative, divide it by the negative that. So, and they want to know to 2 decimal places. So, let's look at this. So time would be 1.67 hours ago. 1.67 hours ago, it was 25% more than what it was now. Okay. Now you got to make sure, and I should have said this on the first video, 6.7 is word problems that use exponentials and it uses logs, natural logs as we just saw and everything. That this section right here is probably the most important as far as what you will see on the final exam. So that's why I'm working every problem. I want you to have something to go back and look at. Okay. So I'm working in sequential order from what you have in your homework. It's just the numbers are different. All right. So let's go to the next one. Um, Only 35% of a carbon-14 in a wooden bowl remains. How old is the bowl? Round to the nearest hundredths, which would be 2 decimal places, and use 5,700 years as carbon-14's half-life. Okay, that's the clue right here. 5,700 years for the half-life of carbon-14. So we're going to find K. K is negative natural log of 2 over. The reason why it's natural log of 2 is half-life, okay? There's some stuff that you can do and to derive this equation, but just trust me, use this equation. It'll be on your formula sheet, so therefore it's very important to do this. So divided by 5,700, so my K is equal to, man, now this right here is probably going to give you scientific notation. It'll probably give you something like 1.216 times 10 to the, or e to the negative 4. What you have to do is you have to write that out, and then you have to expand it, right? So mine came out, okay, mine was as an exponential. I mean, as a scientific notation, it came out to be this, right? E to the negative 4, which meant I had to go one. So I was here 1, 2, 3, 4 places, right? So the green is how it showed up on my calculator. It started here, so 1, 2, 1, 2, 3, 4, right there, right? So that's, and it's negative because there's your negative. It's decaying. So just remember how to do that. Okay, well, they only had 35%. Now let's think about this. Y equals a sub 0 e to the kt. Well, 35% meant that the ratio between what you had and what you started with was what was left. Only 35% of the remaining. So this right here, these two, the ratio of y over a sub 0 is 35%. Okay, so that's why, you know, if you do that, this is going to give me 35%, which is 0.35 e to the negative 0.0001216 t. Now, if you remember the previous problem, you should now know that, okay, I see a pattern. I got an E. How do I get rid of an E, which is an exponential? I got to take the natural log, right? So what I do to one side, I got to do to the other. So these cancel. So it leaves you natural log of 0.35 equal to negative 0.0001216 t. And then it just becomes a basic algebra problem, right? Divide both sides. One more. And what we'll get is, you know, this cancels this, so it'd be t. My time is a natural log of 0.35. I would do that first and hit enter, then I'd hit divide, and then I'd type in this number right here. And what that gives me is, when you do that, it gives 8,633.4056. Now, my calculator set up for 4 decimal places, so if we have to round to the hundredths, then this 5 is going to make that 0 go to 1, so 8,633.41 years, right? Okay, so just kind of be aware of that. All right. Let you kind of take that in for a second right there. Yeah, let me bring that there. There you go. Okay. Now let's look at the next problem. In 4 years, 20% of a radioactive element decays. Find its half-life rounded to 2 decimal places. Now, this is a two-parter. okay? Because the first thing I've got to find is its decay rate. Um, but I don't know its decay rate because we can't use the equation. Um, I can't use this right here. I can't say negative natural log of 2 over uh, half-life, right? The time t and how long it takes to get to its amount, half-life. They gave me in 4 years 20% of the radioactive decays. Well, there's some things you got to make sure you understand, and we're still going to do it like this: y equals a sub 0 times e to the kt. If 20% decays, then the ratio of the final amount over this is how much is left, right? If 20% is decaying, then 80% is still there. And it took 4 years, right? K4. I should have wrote it 4K, but I left it in how it's written here. Well, we know we're going to have to do this, right? Get rid of this. So it's the natural log of 0.8 equals 4K. And then divide both sides by 4. Okay. In doing that, that's going to help us solve for K. So K is going to be the natural log of 0.8 over 4, which is going to give me a negative 0.558. Okay. Now, we've got to now turn around and find its half-life. Okay. So how long is it going to take for this radioactive to get to half its life, right? Excuse me. Okay, so let's think about it. We're going to start the equation kind of again. Y equals a to the 0 times e to the kt. This ratio between the beginning and the ending amount is half-life. So I could put numbers in there and divide. I can like put 2 as the initial and 1 as the ending, and then when I divide both sides by 2, I'd still end up with half, right? So a little understanding is the right side is going to be 0.5. That's the same thing as kind of like what we've done here. Half of it's remaining, so 50% is remaining, so 0.5. E to the negative 0.558 t, and of course we've done this before. We're going to turn around and now we're going to take the natural log, right? And that cancels that, so we have natural log of 0.5 equals negative 0.558 t. Divide both sides now by negative 558. And then what we are left with is this. Time is going to be the natural log of 0.5 over negative 0.558. And when I do the natural log of 0.5, it's going to give me a negative number, okay, divided by a negative number, which is going to give me a positive, right? Which is, so it kind of tells me, hey, I'm going in the right direction. So time is 1.2422. And of course it said, I think, to the hundredths, 2 decimal places. Okay, so time is 1.24 years. Okay, so it takes 1.24 years for this particular radioactive substance to reach half its life. So you should see a particular pattern between these problems by now. They're going to throw a curveball at us real quick. Well, I'll save it for the part 3's video. So this concludes part 2's video of section 6.7.